Hi, let's continue to look at examples where we are trying to evaluate the stability of different systems. So, in this slide, we have basically a system that controls the speed of this bottle filler plant, right? And there is the motor here which controls this screw, and as the screw moves, this the bottles keep traveling ahead, and there is a feedback here and a controller here, and the block diagram is shown here, and we want to find out at in what um, circumstances and for what gains the system is stable. So, as we said before, what we want to do in this case is to evaluate the transfer function of the system. Now, as you can see, it's fairly straightforward that the loop gain is k over s times s plus 2 by s plus 4 times s plus p, where p is another parameter. Okay. Now, what we want to do is we want to write the transfer function. And as we looked at in the previous case, our transfer function is going to be simply g over 1 plus g. Okay, and if we write this, what we would get is k s plus 2 over, it's going to be s plus 4 s plus p plus k s plus 2. Okay, I'll let you work this out and see that what I've written is right. Okay, so this is going to turn out to be ks plus 2, and now you can, so this becomes s square uh, plus 4 plus p s plus 4 p plus k s plus 2, and that becomes equal to k s plus 2, and in the denominator we get s cube plus 4 plus p s square plus 4p plus k s plus 2. Okay, so I think I need to move this a little bit towards the left so that you can see the entire expression. Okay, so that's the expression. And now, what is the characteristic equation of this transfer function? The characteristic equation is this part of the equation, right? And we can evaluate the stability of the system looking at that. So let's do that in the next slide. Okay, I've made a small mistake here. So this is supposed to be 2k. Okay, so we have this transfer function here, and now we want to evaluate the stability of the system. We start to evaluate the stability of the system by making the Routh array. Okay, so how do we make the Routh array? We write s cube, s square, s to the power 1, and s to the power 0 on the left hand side, and then we populate the first two rows of this array. And what do we populate it with? The coefficient here, which is going to be 1. Then we're going to get 4 plus p here, then 4p plus k here, and 2k here. Okay, and now what we want to do is we want to find out the value at this position, right? So how do we find out the value at this position? What we basically want to do is, that's going to be minus 1 upon 4 plus p, and we can write a determinant here, 1 4 plus p 4p plus k and 2k. And what is this value going to be? It's 1 minus 1 over 4 over p, 2k minus 4 plus p, 4p plus k. And that you can write as minus 2k over 4 plus p plus 4p plus k. Okay, so let's put this value here, and what do we get? So let me write it as 4p plus k minus 2k over 4 plus p. Okay, the value at this position is just going to be 0, and the value at this position, and I'll let you verify it, is going to be 2k. Okay, and this is going to be 0. So now if you want to find out the stability of this system, what is the condition? That all the elements of the first column of this route array are of the same sign. And in this case, because there is a positive element here, we want all these to be of the same sign. All these to be positive. So we have 4 plus p is greater than 0, which implies that p is greater than minus 4. That's one condition. Second condition would be the easier one. I'll just take this one. So 2k greater than 0, which means that k is greater than 0. And the last condition is 4p plus k minus 2k over 4 plus p is greater than 0. Okay, this means that 4p plus k is greater than 2k over 4 plus p. Now if we assume that 4 plus p is always greater than 0, then we can say that 4p plus k times 4 plus p is greater than 2k, which gives us, let's just open this out, you get 16p plus 4p square plus 4k plus pk is greater than 2k. Okay, and this means, let's just arrange it in terms of k. Just let's bring k into one place. So you get k times 2 plus p is greater than minus 4p square minus 16p. And let me just kind of write this here. This implies k is greater than minus, let's write 4p and p plus 4 over p plus 2. Okay, so that's our condition for stability. Now depending on the value of p, uh, yeah, so those are our conditions for stability, and I think we can leave this problem at this place.